Next, we'll talk about homogenization and dehomogenization of polynomials. So the setup there is that we have defined the Zariski topology on AN and on PN, where closed sets were affine or projective subvarieties, respectively. And we have, of course, that AN sits inside PN by a particular map that we'll recall in a second. And the natural question is the Zariski topology on that subset induced from the Zariski topology on PN? So does this fit together? And if you try to answer this question, you immediately start asking, well, can we relate polynomials on AN, so polynomials in these n variables here, with homogeneous polynomials on PN? And that's exactly what this video is about, and this construction of homogenization and dehomogenization. So one direction is a bit easier. If you have a homogeneous polynomial in x0 up to xn, you can get some polynomial in x1 up to xn by just setting x0 to be 1. And this is called the dehomogenization of f, denoted f upper I. Note, this recipe also works, of course, if f is not necessarily homogeneous. And in fact, if you do it for all of the f, then you can see that setting x0 to be 1 is a surjective ring homomorphism from this ring to this ring. And this translates as saying that it respects sums and products like this. And then it's in general true if you have an ideal in here, then its image under this surjective ring homomorphism is again an ideal. In particular, if you start with a homogeneous ideal, you get J upper I, which is just a set of all f upper I for f and j. And this turns out to be an ideal in the ring with n variables. Okay, so we went from homogeneous to inhomogeneous elements, and now the opposite way, there you have to be a bit more creative. So let's say we have any polynomial in x1 up to xn. It should be non-zero, let's say, and of degree d, but it doesn't have to be homogeneous. Then we define f upper h, the homogenization of f, by this recipe that we replace all the xi's in the arguments of f by xi divided by x0, and we multiply by x0 to the power d, the degree of f. And then this, if you stare at this for a bit, you can see this is again a polynomial, because all of these denominators, the highest power of the denominator that can appear is x0 to the d, the degree. And then by multiplying with this, you clear all denominators. So you get back a polynomial. And if you spell it out in this explicit form, the only thing that happens is that you have exactly basically the same set of terms as before, but in each term, you just substitute or you multiply this term by some power of x0, namely exactly the right power, so that the full term in the end is of degree d. In particular, you see all of these terms are now of degree d, and so you get a homogeneous polynomial like this called the homogenization of f. And this also has some nice properties, but also some less nice behavior. So if f and g are of degrees d and e, then of course their product is of degree d plus e. And then the homogenization here, by the recipe, you just substitute all of these terms. You have an x0 to the d plus e. And then you can split this term as an x0 to the d times f, and x0 to the e times g. And then by definition, you just get by fh times gh. So it works well with products, this operation of homogenization, but it's not true, and we're going to see an example in a second, it doesn't work with sums. And that creates some issues. So in particular, if you want to take some ideal in these n variables and get a homogeneous ideal in the n+1 variables, what you should do is you should take all the elements of f, which are non-zero, homogenize them, and then take JH to be the ideal generated by all of these things. This is clearly a homogeneous ideal. And it is necessary here to take this ideal generated by all of these things. So let's see an example. So this homogenization procedure is actually not super complicated. We start with this f, and then fh. By definition, it's a degree 2 polynomial, so you have x0 to the 2, and then you substitute these xi divided by x0. And then you see for the first two terms, actually, this doesn't change anything because you have you divide by x0 squared, you multiply, you get back the first two terms. But the last term, which was of degree 0, this gets bumped up to be degree 2. And if you follow the other recipe, you just go through each of the terms and multiply by a power of x0, which brings it to degree d. And then we see if we first take fh and then the inhomogenization, then you take this and set x0 to be 1 again. And then it's clear from the recipe, setting x0 to be 1 just recovers f again. So this is actually always the case. And here we see an example that this property doesn't hold, because you can write f as the sum of two things. It's degree 2 part and degree 0 part. And both of these are, of course, homogeneous. So if you apply the homogenization, it doesn't do anything. But then the homogenization of the sum is not equal to just the sum of the two parts, which would give f, because f really changed. And so we see that this nice property doesn't actually hold. In this vein, you can try in the next exercise to either prove or find a counterexample for some nice properties. Namely, the claims there are, first, if you start with a set of homogeneous polynomials, then if you first take the ideal and then the inhomogenization, is the same as first taking inhomogenization and then the ideal, where the SI is just a set of all dehomogenizations. And the second is similar. You start with some set of non-zero polynomials. Is it true that if you first take ideal and then homogenization is the same thing as first homogenization, then ideal? So there, well, you can maybe start trying to prove it, and then if there's too many difficulties, maybe you will discover that one of these properties doesn't actually hold. Okay, so this was all pretty formal, and now we can return a bit to the geometric side, because as we said at the beginning, we have that AN sits as a subset inside Pn, and this the subset is this U0, the locus where the zeroth coordinate is non-zero. And we saw this map is just given by setting the coordinate to be 1 under this map. And first of all, the claim is this U0 is an open subset of Pn with respect to the Zariski topology, because its complement, well, it's the locus where x0 is equal to 0, so Vx0. So this is a homogeneous polynomial, so by definition, this is indeed a projective variety. So here the picture is Pn has this nice open part An, and then this line Vx0 at infinity. And now the big claim is that the subspace topology on An is just its Zariski topology that we defined before on An. And so we just show kind of two directions. We show if a set is closed in one topology, then it's also closed in the other topology for both directions. So let's first say X is a set which is closed in the subspace topology, which means there's some closed set in all of Pn, such that X is in a section of this with An. So this set in all of Pn, this is the vanishing locus of some homogeneous ideal. Then the claim is X inside An is actually just the vanishing locus of the inhomogenization of J. And for this, well, just observe, points in X are cut out by these homogeneous polynomials in J, and they should also sit inside An. And then if you take the pre-image of such a point under F, so then we ask which points here map to X. And so it's just points x1 up to xn, such that f of this point has the property that all these f vanish on there. But then small f composed with big F, well, big F is just the map which sets x0 to be 1. This is exactly the definition of the inhomogenization. And so we see inside an, this is cut out by all of these fi. And so this is just the definition of VA of ji. So that's one part. The other part is also not super hard. So let's start with something in an which is thoroughly closed, so which is cut out by some ideal inside k of x1 to xn. Then the claim is x is the intersection of this closed set in Pn, so just the homogenization of J intersected with An. And so for this, well, you see X inside An is cut out by these elements G and J. And then the claim is, well, G at all of these points, this is the same thing as first applying F at these points and then the homogenization. Because, well, basically this sets x0 to be 1. And then if you plug this into GH, this actually didn't do anything. We just get back the G. And so again, you see that somehow this set is cut out by the same equations as this set. And okay, this finishes the argument. You just have to maybe write it down for yourself and convince yourself. Okay, so we saw that the closed sets in one topology are equal to the closed sets on the other topology. We've also seen that as a map of sets, this is bijective. And so in fact, this map here is bijective, continuous. It identifies the two topologies. So there's a homeomorphism. And then in the next video, we're going to talk about some topological properties of projective space. Because now that we have this nice open subset AN, we can transfer a lot of knowledge from this to the projective space itself.